You know, see some nice fluid lab experiments from Anne Davaille. And want a longer introduction of that? Want me to mention you were a Yale postdoc too?
But not with you.
That's okay.
Turn out the better.
Okay.
Carry on.
Can you hear me? Oh, okay. Is it okay now? Okay, so good morning. So Dave asked me to talk about heterogeneities in the mantle and their signature, like plumes, pile, dome, a whole zoology of terms that we're going to learn about. And a lot of this work has been done in collaboration with Michael Lebars and Ishiro Kumagai and Kei Kurita at ERI Tokyo. So we're going to look at the fluid mechanics of thermal convection when there is heterogeneities in a fluid and at the signature that we can explain on Earth. But of course it's melt in the mantle, so we're going to see where melt is going on, is entering the problem. So through the origin of the heterogeneities, then we'll get to the observation and then to the thermal convection. So partial melting, I think, is very important because in fact it's the source of the heterogeneities in the mantle. Partial melting and solidification through two main processes. So it can be, those heterogeneities can be inherited from the early stages of the planet, like magma ocean or solidification, but it's also continuously reinjected through subduction, since we are subducting a sandwich of oceanic or millefeuille of oceanic crust, lithospheric depleted mantle called mantle. So first of all, if we're looking at the initial stage of solid state convection, so it's inherited from the magma ocean solidification. So if now I have a liquidus curve that is with this shape compared to the adiabats in the mantle, we're going to solidify first from the bottom and move to the top. Then, as incompatible elements, like for example iron, are going into the melt, the last solid to crystallize on the top will be the one that have the most iron, and so they will be denser than the rest of the mantle. Then you can have overturn of this denser top layer through Rayleigh-Taylor instability, and you end up with a denser layer at the bottom of the mantle. So this has been proposed by a number of authors. Then now if you have a liquidus curve, that is as the one here, so that it crosses the adiabat somewhere in the mid-mantle. So this time you're going to begin your solidification somewhere in the middle of the mantle, and so there's going to be all the top of the layer that is going to crystallize from the top up. But if the melt is also denser than the solid, then you're going to have a basal magma ocean that is going to crystallize from the top down. So again, the solids are going to be progressively enriched in iron, more enriched in iron. And so you're going to end up with a density profile at the bottom of your mantle with a progressive densification of the mantle due, for example, to the iron content. And since this basal magma ocean is, is isolated from the cold surface of the planet, it's going to take a long time to solidify. And so we may have still some partial melt 4 billion years after the formation of the planet at the very bottom of the mantle. So that was the first way of creating a reservoir that is of denser heterogeneities in the mantle. Then we have another process, which is the continuous reinjection through subduction of oceanic crust. So in the on the surface, the oceanic crust is lighter than the lithospheric mantle, but since it's the whole thing is cold, it is very viscous, and so it can be the oceanic crust is entrained by the gravitational instability of the cold lithosphere because it's viscously coupled to it. Now, if we enter into the lower mantle, mineral physics experiments is showing that the density of MORB is in the whole lower mantle is going to be denser than the bulk mantle at the same pressure. So it means that if the system is warming up and so the viscosity decreases, you could have segregation between the dense crust, oceanic crust, and the bulk of your slab and the bulk of the mantle. So in fact, if the time scales allow it, you could build a denser layer on the co-mantle boundary with oceanic crust. So it's really a question of, one, the buoyancy ratio, so the density contrast between the oceanic crust and the bulk, and also the viscosity at the bottom of the mantle to allow the building of this denser layer. Because in fact, you could imagine a situation where, okay, you're segregating, you have your oceanic crust coming down, but that convection is quick enough to re-entrain the whole thing. So that's the first end member. The second end member is that you're building your denser layer, but then you have convection and you have entrainment. Or you can have something in between, and that's what we're going to see. So the observation of heterogeneities in the mantle. So I'm a physicist, and so I have a lot of trouble with geochemistry. But from what I understood, okay, if you have those sort of diagrams, so I want to run, but you can make sense of it if you if you say that in fact you need different heterogeneities in composition, in isotopic composition in the mantle, and then you can explain all those arrays corresponding to the different hotspots. So Dan told us on Monday that even if you consider the aging of material that has been once differentiated on the mid-ocean ridge, you cannot, it's not sufficient to explain the whole range of the observation. Then there is also other observation that is telling us that some material that is brought back to the surface now by a hotspot or Larginius Provence volcanism has been isolated in the mantle for several billion years. So in a mantle that is convecting quite actively, as we're going to see, you cannot do this thing if the mantle is just homogeneous. So then seismology is seeing a lot of different structures in the mantle. So here I've put 3 different tomographic models. So that's the new Berkeley one, that's Ritzemas, and this one I don't remember. Yes, Kustovsky. And so going from the under the surface to the CMB, above the CMB. And you can see on this that on all the tomographic model, the ridges are shallow features, so that you got them in the top part, but then they disappear. We have some blue material so that you can interpret its fast. So blue, it's fast S-wave speed, so that it can be interpreted as cold. And you've got this blue material that can be tracked all the way down to, from the surface to the co-mantle boundary. So in fact, and if you look, for example, on the co-mantle boundary, you've got the impression that the mantle is right now cut in two boxes. So you have two big red potatoes, but you have this ring here of cold material that you can trace all the way from the top to the surface. So that in fact, slabs are giving us the larger length scale of motion in the planet. But within those two boxes, we have slow anomalies, and they're quite large. So it's degree 2. So they've been called the large low S-wave velocity provinces, LLSVPs. And and if, for example, you take here, I've plotted the minus 0.5 S-wave velocity anomaly, the contour, you see that those two big provinces, it's not just a big province going up, it has a lot of structure. If we go further down and we use a different type of seismology analysis, the seismologists are telling us that there is a number of very ultra-low velocity zones, those dark red here features, and that those ultra-low velocity zones are detected mainly on around the LLSVPs. So the velocity of the waves are so low that it could be interpreted as molten material. So that's for the seismology. Oh yes, I forgot to mention that if you look at what you can infer for the composition of the large low velocity provinces, there's some evidence that the material needs to be compositionally a bit different in order to explain, for example, the ratio of the P wave over the S wave velocity anomalies. So we have two big provinces, and there is chemical heterogeneities in them. And at the bottom of the mantle, we may even have some pockets of partial melt. So if now we're looking at intraplate volcanism, so hotspot. So we have the classical hotspots, so like Hawaii, with a long track. So with this explanation that it could be a hot upwelling from deep in the mantle, quite fixed, that is burning its way through a moving plate, and so you have those long tracks. Some of those long tracks are initiating at the big oceanic plateau, so that if you get this plume, hot upwelling vision of a big head, a balloon on the string, well, the balloon is the oceanic plateau, and the impact of the conduit there is the long track. So we have several of them, for example, in the Pacific, Hawaii, Easter, Louisville, Galapagos. And if we look at where they are compared to the LLSVPs, in fact, they are on the outskirts of the large low velocity provinces. I talk about the oceanic plateau, so the beginning of those long tracks. But in fact, if you reconstruct where were erupting those largineous provinces through time, you see, and that's the work, for example, by Tosvik and collaborators, you see that most of the heterogeneous provinces are falling also on the outskirts of those large low-velocity provinces in the last 200 million years. And the last thing about those those long-term hotspots is that, for example, if you look at what is underneath, so for example here underneath Samoa, you always can see now with the latest model some low velocity from all the way down to the core-mantle boundary. But if you look at intraplate volcanism, in fact, you have another family of volcanic tracks, much shorter tracks. So here it's the number of cement in the the volcanic track as a function of their length, their duration in volcanism, and so you have all the long tracks I was telling you about. But then you have a cluster between 10 and 40 million years long tracks, and presently they correspond to here this big South Pacific superswell, because there is also a swell in the topography. So it would be Tahiti, Cook Austral, and so on. And this place is really interesting because if you look on in the Pacific, you have exactly the same kind of province with a cluster of short tracks here, the Darwin Rise. And if you look at the age of the Darwin Rise, it's this cluster here. So and what is interesting is that if you reconstruct where the Darwin Rise was 100 million years ago when it was active, it was on top of this Pacific superswell now. So in fact, there seems to be another type of upwellings with 100 million year recurrence, and that is creating on the surface a cluster of short tracks. So what can purely thermal convection in a solid state mantle can explain of those observations? So that will be the only equation I'll be showing. But we're solving also equations. So in the lab, it's nature that is solving the equation, but there is also a lot of numerical simulation going on the subject. So there is the mass conservation, the momentum conservation. So the engine of the whole thing, it's the gravity force here. The inertial terms are negligible. So because so the Prandtl number, which is comparing the diffusion of momentum and the diffusion of temperature, is very large. So it means that as soon as I stop my motion, I stop my engine. So my temperature differences, I'm going to stop my motions. So this term is really completely negligible, and in fact the chaos in the system is going to come from the heat conservation equation and the advection of the temperature gradient here. So so that the key parameter that we're left with is the Rayleigh number, which measure which compare the engine of convection, so buoyancy force, over the two dissipative effect of momentum and temperature. And so in a planet, this Rayleigh number is 10 to 6 to 10 to 9, and both numerical simulation and laboratory experiment can reach this regime without any problem. So that in fact, if you look at the different regime as a function of Prandtl number and Rayleigh number, so ocean and atmosphere would be around here in this range. If we look at the magma ocean, we are 10 to 25, so way out of what is reachable both by numerics and lab. And then we have also the problem of rotation. But if you go to a solid state mantle, so you have a quasi-infinite Prandtl number, but it's very tractable both in the computer and in the lab. So that it's one of the geophysical systems that where we can have really a good dynamical similarity. So if I'm just looking at convection in a Newtonian fluid with nearly constant viscosity, so the regime, the morphology of the convective motions is going to depend only on the Rayleigh number. And here I've plotted as the different regime as a function of the viscosity of my mantle and the depths involved in the convection. And in fact, so for a mantle of 3,000 kilometers thick and about 10 to 22 viscosity, we see that we are in a regime where we have plumes. So we should have, if the mantle was constant viscosity, we would have upwelling plumes, so that's good to explain hotspots, but we will have also downwelling plumes. And in fact, those upwelling plumes really do a good job quantitatively to explain, for example, the length of the duration of the hotspots, since those plumes, in fact, you can fluid mechanics can give us a scaling for their onset, but also the duration of their life. And if you apply this scaling law to mantle situation, as a function of the viscosity, you will get duration of plumes between 10 and 200 million years. So it's exactly the range that I was quoting earlier. So we have plumes, but we have no cold plates, and we don't have LLSVPs. Then we know also that the mantle has a viscosity that varies very strongly with temperature, so decreasing when temperature is increasing. And in this case, compared to the constant viscosity momentum equation, where you will have this term, this viscous term here, and the engine here, you have to add this term here. So that in fact, if if the total viscosity variation in your system is greater than about 1,000, this term becomes really important and introduce a strong asymmetry in the system. With this time, most of the viscosity variation is taken into the cold top layer, so you're building a much more viscous cold boundary layer on top of your mantle, and then you can have plumes underneath. So there is a strong asymmetry, both in the temperature structure, but also in the morphology of the motion. So you can still have plumes with a head and tail, but now the downwellings are a lot more like fingers or even sheets. So there's been a lot of work on both numerically and in the lab on this type of convection. And as a function of viscosity ratio and Rayleigh number, you can get a regime diagram. And the message here is that if the viscosity ratio is greater than 10 to 4, then you're going to be in a stagnant lead, so that your cold thermal boundary layer is so viscous that it's not going to be involved into the convection. But underneath, you're going to have some interesting regime, especially for viscosity ratio about 1,000, and high Rayleigh number for based on the bottom hot viscosity. So for example, here, we can see that the downwellings are always at the same place, and they describe cells, but you have several plumes that can be episodic into each cold cells. So in fact, if the effective viscosity of my lithosphere would be between 500 and a couple of thousand, a couple of thousand times the bulk mantle viscosity, then in fact it would explain quite well the data with, by saying that in fact, so the large-scale circulation that we see, well, it's just convection of a cellular form of convection due to the cold lithosphere. And then within each of those cells, we can have several plumes, as we see here. And so it would explain, well, what we see on Earth. But
ask out of curiosity, what's the fluid that you were using?
so here it was sugar syrup.
Okay.
But we don't get, so we don't get piles, we don't get molten area, and so on in this type of convection. And there is also the problem of this second family of hotspot. So we really need to get to convection into the interaction of convection and denser reservoirs. So here I'm going to lead you through the different regime that we can get in this very simple initial configuration. It's I have a mantle, but there is a denser layer at the bottom of the mantle. So there have been a lot of numerical work and also experiments, stability analysis, also of the equation. And all this boiled to those 4 parameters here. So we still have the intensity of convection that is going to depend on the Rayleigh number. But then there is really this key parameter here, the buoyancy ratio, which is the ratio of the density contrast of compositional origin divided by the density contrast of thermal origin. So the stabilizing effect over the destabilizing effect. So those two are going to give me the stability and what regime we are in. We have also the viscosity ratio, so the viscosity ratio between the 2 layers and the aspect ratio between the 2 layers. And those 2 parameters are going to be important to give me the morphology. So, in fact, if we look at the Rayleigh number as a function of a buoyancy number, we see that for a buoyancy number greater than a critical value, the system is going to stay stratified. So the thermal buoyancy would never be big enough to counterbalance completely the compositional buoyancy, and so we will have convection into superimposed layers. Close to the critical state, we have an interesting regime with with oscillation, so that we can have really big deformation of the interface and traveling wave, or even oscillatory motions. And then for higher Rayleigh number, we're going to combine those oscillatory motions with the other thermal modes in the system. So I'm going to back up a little bit and just simplify the system. So now we're going to look at just what happened to a plume. So we have a heater here, sugar syrup, so the viscosity depends on temperature. The hot fluid is typically here 100 times less viscous than the ambient. And we're going to heat the system. We can also introduce at the bottom of the tank this orange layer here. It's exactly the same fluid, but we've added a little bit of dye and some salt to increase locally the density, so that the buoyancy ratio is going to range from 0 to more than 1. So first of all, the reference case, buoyancy ratio equals 0. So what is a plume in my system? So you see it developing. So we've seeded the fluid with liquid crystals that are several types that are each reflecting the light at a different temperature, so that all the lines that you are seeing here, they are isotherm. So we're beginning with 23 degree here, ending to 40 in the center. So that's my reference case. Now, for the case of buoyancy ratio 0.4, so going back. So first of all, I have a plume. I heat my system. I have a plume. But you see that at some point, in fact, as the plume is rising, it's losing its heat by conduction, so that the denser orange fluid, that is chemically denser, so at first it rises because it was hot enough to be buoyant, but it reached a level where it has lost its part of its thermal buoyancy. And so even though I still have some fluid going up, I have the core of my plume that is coming back down.
You apply some temperature differences?
So here it's the lab temperature, and here it's a hot source. If I increase again the buoyancy ratio, I still have, so I heat enough to have first instability, but then it reached its level of neutral buoyancy earlier, and so you're left with a dome-like structure, but still this is still hotter than the bulk. You generate a secondary plume on top of your dome. So thermochemical plumes and domes have a behavior that depends very strongly on time. And in this case, as soon as you have a buoyancy ratio typically greater than 0.6, you will have the formation of dome and secondary plume. You can see that you're still entraining a little bit of the denser material, but it's a filament in the center of your plume. So in fact, to understand the whole behavior, the key parameter is the local buoyancy ratio. If I know at each point the temperature and the composition, I can calculate locally what is going to be this buoyancy ratio as the local density difference of chemical origin divided by the local temperature thermal buoyancy here. And you see that, so here we have a local buoyancy ratio lower than 1 for all the blue and greater than 1. So it means that you are too dense to be rising for all the red. And you see as a function for those different initial buoyancy ratio, the structure. And indeed, the critical local buoyancy ratio above which the fluid is going to go down and not up is really close to 1. So now I can do exactly the same experiment again, but back to a more mantle-like setup with heating from below, cooling from above. Here the buoyancy ratio, the initial buoyancy ratio was 0.45, and the Rayleigh number was 10 to 7. So as you see, we have again those big thermochemical dome developing, going up and down. You get also secondary motion on top of those domes. And it's a very time-dependent system. But now when I compare those kind of features with the big structures that are in the LLSVPs, they look a lot more alike. So those experiments in the lab are quite long. It's typically between 2 hours and a week. So it's viscous fluids, so you have to be patient. So it has been accelerated here. So you see also very sharp structure. Okay. So varying the different, I told you, varying the SP ratio, varying the viscosity contrast, and the buoyancy ratio, you have all sorts of different morphologies. And so I'm not going to detail all of them. I won't have time. But, but there is two good news. The first good news is that, so I told you there have been a lot of experimental and numerical work, and they're all plotting in the same regime diagram. So everybody agrees that for buoyancy ratio greater than 1, you're really in the stratified regime. So you're just going to have entrainment at the interface. For buoyancy ratio between 0.4 and 1, that's where all the interesting doming behavior is occurring. And you can have dome, piles, ridges, depending. So all those terms define different morphology, but they're all into the in the same narrow buoyancy ratio range. And then for buoyancy ratio typically less than 0.1, it's like an homogeneous thermal convection. But then in the mantle, if you plug the numbers of the mantle into this buoyancy ratio, you see that you can get all those different regimes only with density heterogeneities of compositional origin between 0 and 2%. So 2%, I'm told that it's quite easy to do in the mantle, so that we should expect at one point or another all those different features. Just something about the dome and the ridges. So in the lab, what I've shown you, there was no dependence on of the chemical density anomaly on depth and on pressure, of course. But there have been some very interesting work that we're dealing with more mantle-like material, where now the density anomaly change with depth because of pressure. So in this case, you can reach, in fact, your level of neutral buoyancy. In fact, this level of neutral buoyancy depends, is still given by the buoyancy ratio, but depends, but it depends on pressure. And because of this, you can have some very interesting shapes, like those piles here, with very, very vertical and sharp interface. Again, here you can have a level of neutral buoyancy that is really extremely flat. So in the lab, the only thing that we can do is to introduce 2 layers of different, densities, so they will stay stratified. And you see that in this case, you can have a plume coming up. It's going to be delayed or stopped at the interface, and you're going to have, but still it's hitting the upper layer, so you're going to have the generation of secondary plume. And in this case, you're going to have several of them, so it's a good way to generate a cluster of secondary plumes. So that if I'm going back to the second family of hotspot, this hotspots cluster that we could see, for example, in Polynesia, I could explain it by one of those thermochemical domes that could generate several hotspots on top of it. And in this case, we predict that those domes have a recurrence. So they're going up, leaving their heat, down and up again. And if we apply the scaling laws for this recurrence time, we get, if I have to have 100 million years recurrence time, it means that the viscosity of my mantle is between 2 and 6 times 10 to the 21 Pascal seconds. So this is not very far from the estimate of the viscosity in the mantle. By the same token, we have also scaling laws about the density, the temperature anomaly that the dome must have to be able to rise. Or we can invert, saying, okay, in the Earth, usually the density, the temperature anomaly that we see for interplate volcanism is about 300 degrees Celsius. Then, I can say that the chemical density anomaly was typically less than 1%. So, so we can indeed explain by thermochemical convection doming in the mantle. We can, and we should expect different type of upwelling, such as the regular classical long track plumes, but also doming and secondary plumes, or even ridges at the bottom of the mantle. There is another thing that fluid mechanics is giving us, and it's the spacing between those instabilities. And you can tweak the parameters in all the way you want, but you will never get a spacing that is more than 3,000 to 4,000 kilometers, which means that each of the LLSVPs contains several of those instabilities. So we don't, LLSVPs, it's not a big instability going up. It's several of those instabilities, and each of those instabilities are probably in a different stage of formation or development. So we can play the exercise of, of looking for those instabilities. So, for example, in the Pacific, we have Hawaii, long track. We have Galapagos, Easter Louisville. Okay. Then I showed you that the Tahitian superswell here, it could be another one, another instabilities. Over Samoa, well, so fluid mechanics is telling me, okay, you find 5 of them, but with this geometry, you should have one here, probably one here and one here. Well, if you're looking in the tomography and the volcanism, so there is Samoa, so it would work. Here, there is nothing on the surface right now, but if you look at the tomographic model, they see something going up. So this one is accounted for also. And this one, and this one, in fact, I don't have time to tell you about it, but it exists also, but this time it's at the stage where it's going down. So you're not going to see it as you're not going to see it in the tomography as a nice red dome coming up. But for example, if you look at the geoid, like Cecilia Cadio did, in fact, you see a signal that can be interpreted like something is coming down. So in fact, we are on the down going on one of those instabilities. And you can do exactly the same exercise for the for the Atlantic box. So for example, under the Capa Verde, Canary, Azores, you could interpret it as another of those dome plus secondary hotspot cluster, and so on. So it seems that fluid mechanics is predicting really well what we can see in the mantle. If we're going to full geodynamical modeling with 3D numerical calculation, so here it's a work by Alan McNamara, Sigizong, and Garnero, and they've imposed on the surface the history of the plate for the last 120 million years, and they're looking at, and then you're hitting from below, and you can see that with that convection and subduction is really delimiting again those two boxes. So in fact, your hot material is really pushed around by the slabs, and that's what is defining this large-scale degree 2 features. But then you have all the different morphology within each of those LLSVPs. Another very interesting thing that they were able to see was if they focus at the LLSVPs themselves, the hottest areas are really on the edge in their simulation, and that would agree quite well with the formation of ULVZ, so that could be interpreted indeed as molten material. So a last thing I wanted to tell you was that we are able also to get to the entrainment rate, the destruction rate of those density heterogeneities. And if you have a situation where, for example, you're stratified locally, but you still have those plumes coming up from the interface, then you're going to entrain by viscous coupling part of the lower layer. The entrainment rate depends strongly, of course, on the buoyancy ratio. If the buoyancy ratio is very big, then you're going to entrain very little. It depends also on the viscosity ratio between the two fluids. But the story for the story is that finally you can entrain only a few % of the lower layer. So only a few % of the plume material will be coming from the lower layer. In the mantle, typical sizes would be a few kilometers at most. But on billion years' time, you can still erase a reservoir if it's not too big. So here, this is the lifetime of a reservoir just above the co-mantle boundary as a function of the chemical density contrast. If the convection in the mantle above it is with the Rayleigh number, say about 10 to 7. And we see that for for density contrast lower than 3%, indeed, thermal convection is able to erase a denser bottom layer. So it gives us some bounds about what those chemical heterogeneities could be if we want them to survive until today. And so convection, finally, thermal convection, even with a denser reservoir, it has always a progression. I mean, it's always toward mixing. You may start stratified, but it's going to eventually evolve through completely mixed mantle. But right now, we're probably into this very messy convection. So there is I wanted to show you just 2 slides about the problem of the replenishment of this denser reservoir through subduction. And there has been almost no experiments with that, but the numerical simulation have been very active in those last 10 to 20 years to try to understand what's going on. And indeed, you can, depending on the buoyancy ratio between your oceanic crust and the bulk mantle, you can make piles. You can even mix some of this oceanic crust with more primordial material. But but if you look quantitatively at the different studies, they still do not agree on the details and the time constant. So I think that for this particular problem, which is really a difficult one, there is a lot more work to do. So as a conclusion, so we've seen that there are a lot of heterogeneities in the mantle, and this is because of partial melting, either initially or continuously through subduction. A lot of observations are pointing anyway in towards those density anomalies. But thermal convection in an homogeneous mantle is capable of producing the large-scale cold wavelengths of the convective motion in the mantle, so plate tectonics. It's really those 2 boxes, it's really a plate tectonics mode. And it could explain also the fact that we see plumes on the edge of the long-lived plumes on the edge of LLSVPs. So that you don't need chemical heterogeneities to explain those 2 things. But you need, I think that you need chemical heterogeneities to explain the upwelling zoology, to explain the LLSVPs and their history through time and their morphology. But convection is anyway able to erase about 3% in density contrast over the history of the Earth. So now what next? I think that we need a lot more work on the replenishment issue and how the oceanic crust segregates, can segregate in the mantle. And we need a lot about the initial state of the mantle. So how does the magma ocean solidifies? And then we're back to partial melting. Thank you.
We have some time for questions.
In the experiments where you'd included the dense layers, did
Yeah.
you see evidence for the secondary plumes localizing to the boundaries of the piles, like the margins?
Actually, yes. Let's see. So when we have doming, so either we had a dome that at its level of neutral buoyancy would spread enough to be able to generate several plumes. So here it's, okay, 1 plume, this is the 1 plume and a center section, cross section, and we're scanning the tank before and after the plume. So you can see that we have several of them. and they're usually they first originate at the on the edge, and that's because that's where you have the lateral boundary discontinuity. So here, so we would observe like this, because that's here that you have both a morphology discontinuity, but also a thermal discontinuity. So that's where the instability is going to start first.
And is the lateral thermal discontinuity, is that because it's the edge of the tank?
Yes, exactly.
So in a wider system, would you still expect that to occur, or is it sort of an artifact of the finite width of the experiment?
No. So I can get this in a small tank, but also in a really big tank where I have only one pile. I will still get preferentially plumes on the edge. And that's because of the mechanical and thermal lateral heterogeneity. So that's where you're going to localize your plume. So it's valid for secondary plume. So of course, if the pancake here is big enough, you can have also one in the middle and so on. But it's also what explains there. That's also what explains, I think, that all the long-lived hotspots, they are on the edge of the large velocity zone. So there is, because you've got all the cold downwelling coming there and spreading, so that in fact they are localized where you have again. So if you have the LLSVP, you have subduction. Again, you have a strong thermal gradient and also a mechanical boundary. So that's where you're going to localize your instability. There can be others elsewhere, but those ones are going to go. And they're also the ones that are going the most stable, because in fact, as long as you have a slab coming and you have an edge here, well, you're going to fed your instability. So that's also why they're much longer duration.
Rich, you have a question?
Yeah, sort of a silly question, but
There's no
I
silly
hope it's
question.
really silly.
no, it is a little bit. So can we think of these LLSVPs as the sort of continents of the bottom of the mantle? And also, given the way the solidus kind of curves backward, or you said the liquidus curves backward, but maybe the solidus also curves backward. Could there be other kind of analogous features at the bottom of the mantle as there are at the top, where partial melting occurs because of compression rather than decompression?
Well, so for the partial melt, I think that for the moment it's mainly the ULVZ that people are thinking about. LLSVPs as continent. Well, as far as actually, okay, if you have zones where it's really denser, then yes, yeah, it's like a continent. But it's also a lot hotter. So in this case, you're going to have probably a lower viscosity. And that's why, in fact, when you have a more viscous instability encountering less viscous material, it's the more viscous that is winning. So that's why the the distribution of the LLSVP is really depending on the distribution of subduction. And so for the moment, for example, there is only 2 big LLSVPs, but if you look closely, there are also other zones where you have some low velocity. And I think that this configuration should change through time. I mean, if we have suddenly a subduction that is beginning in the middle of the Pacific, when the slab is going to hit this, is going to reach this area, yes, compositionally denser, but also probably a lot less viscous. It's just going to push it around. And so you're going to, so they're probably through time, I think that there can be more than 2 boxes. It's just today.
Can I ask a question, John, or should we move on?
You got time. Good.
Okay. One quick question. I'm going to ask a question. One of your dimensions in your parameter space is not with regard to heating mode. I mean, your experiments are all bottom heated.
Yes.
Right? And I'm wondering, in terms of the survivability of these anomalies, it seems like if you're heating it from below, you're really driving heat through these big anomalies and driving plumes through them. Whereas if you're more dominated by internal heating with stronger downwellings and slabs, which tend to gather up these piles and confine them. In addition to that's also controlling the replenishment rate that you said that it's not well studied, but that's the main replenishment rate from oceanic crust that's filling them up again. So I'm wondering, how does the survivability of these depend upon the heating mode, whether it's heated from below relative to internal heating? Do you have any thoughts on that?
Well, actually, yes. I think that quantitatively, it's going to depend, of course, on the heating mode. I think also that when in the mantle we're speaking about chemical heterogeneities and density heterogeneities, it should be attached to a different content in radioactive heating. So I imagine that those piles are also probably more radiogenic. And so the heat, so I think that we should really do more work on quantifying this importance of internal heating. But still, I mean, even when you are heating from below, you see that the morphology of the piles, it's really driven by the cold viscous stuff. I mean, so you still, I think that qualitatively you're still going to have the same range of morphology and all that. Quantitatively, it's going to change. Yes, I think so.
Okay, we should move on to the next talk. Sure, you want to